Good evening from the Way Happy Studios. This is Mr. Meyer on a way late night trying to figure out what polar coordinates are. So let's talk. So the first thing you want to notice is you've always been graphing on what we call rectangular or Cartesian coordinate system. That's your usual XY thing. And you've gone out and you go out and you plot 4 1. You're like 1 2 3 4 up 1, and you plot a point and see it kind of makes a rectangle, so it kind of makes sense that it's the rectangular coordinate system. Well, a little heads up, there's another way that you could graph points. There's another way, and it's called polar coordinates. And what it does is it says, hey, if you want to talk about a point, a cool way too is you measure the angle that point is at, and you tell me how far away it is from what we call now the pole. We would call that the origin in the other one, but now we're going to call it the pole. So what you do is you measure how far away it is, and you tell me at what angle it is, kind of like magnitude and direction, right? But it's called the distance and the angle, and that's how polar coordinates were created for graphing. So you can plot a point just by knowing the angle and how far away it is from the pole. Another thing you might want to know besides the pole is that the x-axis is now called the polar axis. So we talk about measuring the angle in standard position. We talk about measuring it from the polar axis. Now, people will present polar form to you in r theta rather than xy, so they will do r theta. Now the funny thing is, usually when I plot points, I work backwards. I usually stand at the pole, look in the direction of the angle theta, and then I travel r units out to it. So let's go ahead and talk about actually plotting one of these things, or I guess 3 of these things. So let's do the first one. The first one, I'm going to look in the direction of 4 pi over 3. So that's a little bit past pi. So again, you got this is 0, you got this is a half a pi, and this is pi, and then this is 2 pi. If you don't know where 4 pi over 3 is, here would be my hint. Make everything, let me get rid of half a pi, make everything in thirds. So this would be 6 thirds. So this would be 3 thirds. And then right in between 3 and 6 would have to be 4.5 thirds. And now I should know where 4 pi is. Oh, it's like down here somewhere. So that's the direction of 4 pi over 3. Now remember what you do on polar. You stand at the pole, so you're standing here at the pole, right in the origin, the middle. You're looking in the direction of 4 thirds, and you will now travel 3 units out in that direction. So traveling 1, 2, 3 units, that is where this point is, right there. And that is the coordinates, or that is the graphing of the point 3 comma 4 pi over 3. So you see, it's not too bad. The big trick is you got to stand at the pole and you have to go in that direction that it tells you, because there are negative numbers, they're just not like you're used to. So let's try the next one, right? If I try the next one I got here, I'm going to look in the direction of 3/4 of a pi. So if this is pi, and then this is 2, that would be 4/4, and this would be 2/4 then, what we call a half. Then 3/4 would be right in between it. So you're like, oh, it's out in this direction somewhere. So sweet. Now remember, you're standing at the pole and you're looking in that direction, but now you need to travel -1 units in that direction. So instead of traveling forward, you're going to travel backwards 1 unit, and that's where your point is. So you're looking in the direction of 3 pi over 4, but you travel backwards because of the -1. So now you might see that's a little crazy, right? Because you're like, oh wow, I was looking in 3/4, but then I went backwards because of the negative. That's just the way it is. Not too spooky once you get the hang of it. How about this last guy? This last guy, notice I did a negative angle. So all that means is go in the direction of -45 degrees. So we know that this is 0, so we know this is -90. So -45's got to be right there in the middle. And I guess I don't really always need a solid line, because that's not actually what we're graphing. We're graphing a point. So here is -45. And where is the point? Well, you're standing at the pole, you're looking in that direction, and now travel out 3 units. So count out whatever you think is 3 units, and wham, there's the point. And that's the exciting part of polar graphing. Now, the one thing you might notice is that I knew exactly where the point was and I graphed it. So every polar coordinate pair tells you a very unique point. But the weird thing is, every point is not unique. In other words, I could describe those points in a bunch of different ways, right? Like one of the ways, we just graphed negative 45, that last one we did C. We did negative 45 degrees, and then we went 3 units. Well, what if I decided to measure the angle this way? If I added a full 180 to it, then I would have just gone negative. So I could have also said negative 3, and then adding 180 would be what, 135? So another way I could have told you that point was I could have said, hey, look in the direction of 135, and then go backwards 3. And you would have been like, what? Crazy. So that's another way to do it. Or let's add a full revolution, right? Why stop there? We could add a full revolution, or we could add 2 revolutions, and we could continue to give the same point different coordinates. So now you might notice, as I increase my screen, didn't know I was going to give me a full screen, there are many ways to describe a point. So here I ask you, if I give you a point, can you tell me all the polar coordinates of that point? Well, sure. Let me graph it first. And let me go out pi over 3, which is, in this direction. So here's pi over 3, 60 degrees. And let me go out 3 units. 1, 2, 3. So I'll make a big old blue dot. And there is our answer, right? Well, again, there's tricks you can do. And you see them at the bottom of the screen. I don't think I got them all the way on there. The trick is this. You can continue to add just 2 pi's, as many as you want, and you still get that same exact point. So I could take 3 comma pi over 3, and I can just take pi over 3 and just keep adding 2 pi, as many as I want, and you will always get that same exact point. You can subtract. N can be negative. You can subtract nice revolutions, and you would still get that same graph, so it doesn't matter. So any of those will plot that point. Also, you could go on the other side of this thing, right? You could only add a pi. So you could add 180 degrees, which is pi. And that would give you, looking at the pole, looking out in this direction, so you would go in the negative 3 to go back to that point. So another thing you could say is, hey, take negative 3, take pi over 3, and add any odd number of revolutions, 1, 3, 5, or 7. So that's why you have this 2n plus 1 pi revolutions. And that would give you any coordinates, but with a negative r value, because you would be facing the other way. And just like that, you're graphing polar coordinates. So let's ask you a question and see what you think. All right, nice work. Now I bet you're thinking the same thing most people are always thinking. I spent all that time graphing in rectangular coordinates. Why are we switching to polar? Well, A, it's fun, and actually a lot of surveyors use it. Whenever they have to cover huge distances, they actually will, you'll see them out in the streets or whatever. You'll see them, one guy's holding a little stick and one guy's holding a computer, and they're measuring angles and how far they are. They're using polar coordinates for measuring. But I bet you're thinking, I wish there was just an easy way to convert it to x and y. And that way I could just graph it, or if I could take an x and a y and convert it to polar to make Meyer happy, that would be great too. Well, good news. This is why we study trig also, right? Say you got a coordinate graph and you plotted the point x, y like I did over here on the right side. How on earth could I change that to polar equations? Well, I could find this distance. I wanted to be in red. I could find this distance, right? Because I know the x and I know the y. I could find how long that line is right there, the r value, by just doing a squared plus b squared equals c squared. So let's call it x squared plus y squared equals r squared. So we have a formula that would relate x, y, and r. And guess what? If we want to find this angle, I think everyone knows that that's just tangent of y over x. Hey, look, we just found another equation. Is that crazy or what? And it works the other way that you saw in vectors. If you want to find component form of something where I give you the magnitude r and the angle theta, if you want to convert that to x and y, you just use r cosine theta and r sine theta, and you got yourself x and y. So wham, we're done, right? Finished. Good. So look at this. Find the rectangular coordinates of the points with the given polar coordinates. So these are polar coordinates, and I got to convert that to rectangular. Well, a piece of cake. I'm going to tell you that the x value is just 2.5 cosine 17 pi over 4, and the y value is just 2.5 sine 17 pi over 4. Grab a calculator if you like and punch it in and see what your x and y coordinates are going to be. Right? Make sure your calculator is in radians mode though, because when you click that cosine button, you better be in radians. And you've got the coordinates x and y, and you can graph it on your good friend, the x and y graph. Same thing over here, but now you got to make sure your calculator's in degrees. You're just going to type 2 cosine negative 200, and it's going to give you the x value, and you're going to graph or type in 2 sine negative 200, and it's going to give you the y value, and you'll have plotted your point. And then going the other way, if you want to find the polar coordinates, if you are given the rectangular, well, you got those other two formulas, right? We know that if you want to find out what the heck the r value is, you could just do 1 squared plus 3 squared. And if you figure out what that is, I got, what is that, 1 plus 9 root 10? And on a calculator, I just figure out the arctangent. I'm sorry, not the arctangent. I set it up as tangent equals 3 over 1, and now I arctan it and get the angle is whatever the heck the arctangent of 3 is, and it will give me the angle. If you want degrees, put it in degrees. If you want it in radians, put it in radians, and you'll be given the r theta. Again, be a little careful because notice we are arcing, right? We're hitting an arctangent button, and you have to remember way back is that arc cosine lives in these two quadrants, and arc sine and arc tangent live in these two. And so if your coordinates were in an area where arctangent can't handle it, like say you're plotting this point down here like you are in example B, when you do arctangent, your calculator is going to give you the reference angle. It's going to give you this angle. And so you're going to want to make sure that you figure out what the entire angle is. So again, if I was going to do B, I'm going to let you do the calculator punching because I don't need to sit here and have you watch that. But if you're going to do that, all I would sit here and do is figure out that r is 1 squared plus 2 squared square rooted, so root 5. And the angle is just the arctan of, what is that, 2? And when I grab my calculator, be careful, it's going to give us a reference angle. So nice work, and you got it converted. And then the fun part is that you can convert also equations. So not only can we convert just regular old points, we can convert equations too. And again, you use these 4 famous formulas that you kind of already knew, but here they are again. And now look, so it gets really tricky. When I want to look at this next example, I want to convert this polar. I have no idea what this polar graph looks like. You can change your calculator to polar mode, type it in. It's kind of neat. You'll see it and you'll be like, wow. And I'm sure, and we'll do that in class. But if I want to know what it is without a calculator, I need to convert it to x's and y's. Sorry about that. And hopefully I will be able to know what the graph kind of looks like. So here we go with the conversion. Now there's a big trouble. Notice that I have r equals 4 cosine. I can't convert that to x's and y's. I have this equation, r cosine theta would be x, but I'm missing an r on this side. So guess what? Let's give it an r on that side. Let's just multiply both sides by r. And if we do that, we get the 4r cosine theta, which we can get the r and theta out and change it to 4x. And that was actually good news because it made an r squared on the left. And look at the r squared over here. You get x squared plus y squared. And all of a sudden, you have created the equation that is represented for that. It apparently looks to be a circle. And if you wanted to go a little farther, you could actually find the equation of the circle. You'd be like x squared plus y squared, oops, I guess I should do minus 4x plus y squared equals 0. And then I could complete the square. Half the middle number is 2, squared is 4. Add it to both sides. So x squared minus 4x plus 4 plus y squared equals 4. So that was me completing the square and adding it here and adding it here. That would make this factor to x minus 2 squared plus y squared equals 4. And I could be like, oh, look, it's a circle whose center is at 2, 0, and its radius is 2. And you'd be like, wow, that's awesome. So there you go. I know that this equation is just the polar equation for a circle who's got a center at 2, 0 and a radius of 2. How about going the other way? Can you convert the x squared plus y squared equals 9 to the other form? Well, we know this is a circle, so what would it look like in polar form? Well, we're just going to work this whole thing backwards, right? I'm going to FOIL this out and get x squared minus 6x plus 9 plus y squared equals 9. I'm going to move that 9 to the other side and have x squared minus 6x plus y squared equals 0. And at this point, you got a couple of options. I would kind of like to move the 6x to the other side, so I have x squared plus y squared equals 6x. And now remember what our whole goal is. We're trying to get rid of all the x's and y's, and we're trying to get r's and thetas into this equation. So you look over at your little cheat sheet over here, and you notice that x squared plus y squared, hey, that's just r squared. And you know that x is just r cosine theta. And if you can look at your answer and have no x's or y's in it, you know you've done your job. And so you're like, I just converted rectangular coordinates to polar coordinates, and it was fun. Good jobs. All right. I'll see you in a minute. Nice effort on those ones. Like to see you trying like that. All right. So now we got the real life part of this stuff that everyone likes to have, right? If you had to find the distance between two polar coordinates, tell what's going on, right? You have a huge distance to cover, right? You're building a bridge or something like that. And so you go out and you would measure, you can't measure across the water because, oh, it's too unsafe. Here, I'll change this little drawing here. There's like water right here. And we're going to build a bridge along that track right there. This is going to be our bridge. And so what you could do is you could have a survey guy standing right here, and you're standing here at the pole, and you could measure that distance, and then you could measure this other distance. Say there's another survey guy at the other town, and he's across there, and we could measure that distance with like a laser or something, and we could get the angle between them, and because of that, we would be able to draw a right triangle and do the law of cosines, or not in a right triangle, draw a triangle, do the law of cosines, and figure out that distance. So polar coordinates are really nice. So polar coordinates help us by we use the law of sines or law of cosines to solve. And all we usually have to do is find the angle between the two sides. So make sure you graph every single one of these before you actually try to do it, because sometimes you get misled into what your actual angle between the two is. So let's see. I got 110 degrees, so remember what I'm doing. I got to look in the direction of 110 degrees, which let's say is out this way. And when I'm looking at that, I'm going to go 8 miles out. So boom, right here, this is 8 miles. And then I'm going to plot the other point, which happens to be in 15 degrees. And there's 15 degrees. And it is, 5 miles out. So boom, right here, 5 miles out. And I want to know how far apart are these two planes. I want to know this green line right here. And so there's a lot of ways we've done it, and one of the easiest ways probably right now would be law of cosines. So notice I can figure out this angle between them. That angle between them is just 110 minus 15, so that's 95 degrees. So I got my angle between them is 95 degrees, and I got the two sides. So remember that formula. It was, let's call this x. The unknown side for us is equal to the two sides added together minus 2 times those two sides times cosine of the angle between them, in this case 95. And now I'm going to grab my calculator and I'm going to type all of that in, and I'm going to square root it, and I'm going to get the answer of how far these are. And as you can see on here, I got it all typed in. And so I put in the log cosines, I got 95, and then I square rooted it, and I got 9.8. So I can tell you that these two airplanes are about 9.8, what were we in, miles apart. And that's it. Enjoy Polar. I'll see you tomorrow. Stay happy.